Evening, everyone, and welcome to session 19 of the data science program. I'm happy to have every one of us here once again for the 19th time, or rather 20th time. So basically, we are going to continue from where we stopped in the last class. I hope everyone is doing very well. I hope you all had a blissful week, and it has been going very well on your end. I hope you're also understanding and grasping everything we've been doing so far, and you've been gaining clarity on all the topics we've treated so far. And so we're going to just continue from where we stopped in the last class, and hopefully we cover what we have to cover today, because we literally don't have time on our side. All right. So before I proceed, I would just like to hear from I don't know if my assistant is on the call right now, but if he's around, I would like to know if he has anything to say to us. And if not, I would also like to hear from the class rep and the assistant if there is anything that they have to say as well before we proceed with class. So Gideon and Nigeria, do you guys have anything to say? And is there anything I'm missing that I actually have forgotten? You can just bring me back to it, or help me remember them.
Hello. Good evening, sir.
Yeah, good evening, Nigeria.
Thank you. How are you doing today, sir?
What do you say? I can't hear you.
I said, how are you doing today, sir?
Okay, yeah, I'm doing very well. Thank you very much. Hope you're doing very well as well.
Yeah, I'm doing well. Thank you, sir. So far, nothing from my end. The only challenge was yesterday. A lot of people could not access the site, so they were working on it. But it was rectified today, and they sent us like messages and all, and we let everybody know on the group too. So that was like the only pending issue. If anything comes up, we'll reach out to you. But for now, that's the only thing, and it has been rectified.
Okay, yeah, actually, Gideon called me today regarding that. So I can reopen the assignment for submission, because I think it affected submissions, and some persons were unable to submit. So I think the assignment should be reopened. It will be reopened till 6 p.m. And once it's 6, it is going to be closed back. So those that were unable to submit yesterday can submit now. All right. So let's get straight to it. So I'm gonna share my screen. Okay, so just give me some seconds. Let me bring up the material that we have. So I've sent the materials for this week's class. Should be on the materials and resources group. So for those that are yet to see it, please just head over to that group, and then you're going to see the material we'll be using for this week. So today we'll continue with logistic regression, and I'm going to be sharing my screen in a bit. All right. So please, can everyone confirm, or can anyone confirm if they can see my screen clearly? All right. That's great. So we are going to look at logistic regression today. Okay. So we started with machine learning already. So this is the second week of machine learning, and we've looked at machine learning generally, what machine learning is. I've introduced us to machine learning, and that was on Saturday. Then on Sunday we looked at the first ML algorithm, which is linear regression. So basically, we introduced linear regression. We looked at the conceptual part of it. We tried to explain some of the concept and some of the things that you needed to know but that you need to know as regarding linear regression. While I explain linear regression, I also made mention or explained some concepts that are not specific to linear regression, right? So, and those explanation from linear regression class, they are actually transferable or can be applied to every other thing we are going to be explaining moving forward, right? So if you didn't attend the class, or if you didn't get that class, if you didn't understand what we discussed, I would urge you to go back to the video. If you've not, I actually believe most of us, a majority of us, should have gone over that video. All right, so you don't have things piled up so you don't have things piled up for yourself. So we've looked at linear regression. We looked at the formula for linear regression. We talked about what each of these parameters here mean. All right. We also looked at the types of variable. And these types of variable, they're not necessarily specific to linear regression. They're just variables that you use generally in ML. So these are notations that you need to know. So we looked at dependent variable and independent variable. We looked at the different ways to the different notations, right? So we can call dependent variable the target variable as well. We can call it the output. So we looked at all these things and we tried to give you an understanding of these concepts. And we moved on to looking at regression line. I explained what regression is, and I explained what regression line is as well. Right? I said that the aim of linear regression is to get a line that best fits our data. So that is your line of regression. All right. So the regression line is a straight line. It has to be a straight line in the case of linear regression. Right? If it's any other kind of machine learning algorithm, it might not necessarily be a straight line. But for linear regression, it's actually a straight line. So that is something we talked about as well. So I gave us some examples, demonstrated, explained it with some of these examples that we have here, right? So we also looked at the types of linear regression. We looked at simple and we looked at multiple, and we actually said that this is due to the number of independent variables as well, right? So for simple, it has just one independent variable, and for multiple, it has multiple independent variables. All right, so we now looked at the evaluation metrics, right? The things that we use to assess and evaluate our model. All right, so we looked at several of them. We looked at mean squared error, root mean squared error, mean absolute error, R squared, and we looked at adjusted R squared. So I looked at how we can find a balance when choosing the right metric. We looked at several of them. We looked at error magnitude, outliers, model complexity, and then we wrapped up with the assumptions of linear regression. Okay, so I explained, or we looked at the different assumptions that you need to have before delving into using the linear regression algorithm. So that was what we looked at in the last class, and I believe this concept or this theoretical aspect should be clear enough for you by now. So when we start the implementation, you shouldn't have much problem understanding what we are doing. So it's going to even make a lot more sense for you if you understand this. So if you still don't understand it, please still go over the video. There are some persons we learn differently. All right, there's some persons that they understand and assimilate on the go. There's some persons that will need to go over what was said to kind of assimilate better. There's some persons that will need to take their time out. So just try to understand yourself and adjust your learning format, right? So the fact there is that there is nothing that you can't understand. That is just the truth. Unless you keep lying to yourself that you can't understand it. And yeah, I call it a lie because there's really nothing you can't understand, because our brain is made up of the same material, right? So if you don't want to use, if you tell yourself that you can't understand it, then there's no way you would, there's no way your brain will cooperate. But if you tell yourself that, okay, I can understand this, but I just need more time, or I need to take it step by step because this is how I actually learn. That's a different thing entirely, right? So you take that approach and that strategy, and definitely you would assimilate and you understand it better. All right. So don't feel discouraged. Don't think this is way beyond your capacity. It is definitely not way beyond your capacity. This is something that anybody can learn. I trust me. This is something that anybody can learn if you really want to learn it. So that's it for linear regression. Then we're going to jump straight into today's class, which is logistic regression. But there's really something I want to show us quickly before we go into that. In the last class, I wanted to demonstrate something, but I couldn't pinpoint the exact website for it. And luckily, our assistant rep sent or posted the link on the group chat. So I don't know how many of us have interacted with it, but let me just do a quick survey. So how many of us saw the link to this particular website now? How many of us explored this? I just want to know if anybody saw that particular link. Anybody? Did anybody see this link or open this website at all? Okay, fine. Because of time, let's just dive right through. So this is a diagram, a visualization that will basically help you to understand what is happening that will basically help you understand what's happening in linear regression. So right here we have our plotted data. Right, so all this blue dot here, can everybody see the screen? Can everybody see the chart that is being displayed on the screen right now? Please let me know so I move on with it. Can everyone see what is being displayed on the screen? All right, fine. So what we have here, we have your x and y axis. You have your x axis here, and you have your y axis here. So these are the data points, right, that are plotted. Okay, so each data point has a y value and an x value, so it's being plotted on the chart. So now, in linear regression, what you're trying to do is to get the best line, right? So you're trying to get the best line, and the algorithm will try to do that until it achieves that particular goal, right? And the way it does that is by using minimizing the error, and the way the error is calculated is by using any of the error metrics that I explained earlier. Okay, so what we have here, we have SSE. So this is a very simple error, right? This basically means sums of square error. All right, so this sums of square error is basically you summing all your error and squaring them. So this is we don't use this in evaluating our model, but this is just a very basic way to get your error. All right. So you can see that the least error that we can achieve in this particular data is 16.35663. All right. And this particular line that we have here is giving us this error here, right? 19.11. So what linear regression will try to do is try to match or try to bring this error to meet at least the lowest possible error that we have here. All right. So if I tap on this show regression line here, you're going to see that we will have a blue line appear. This blue line that is appearing here is the line that best fits our data. Okay. So when you run your algorithm several times and try to minimize the error, it's going to converge at this point, and we are going to get this regression line. So this is going to be our model. So you can see now that this particular line would be, it is going to be changed until you get to this particular point. That is the goal of linear regression. Right, so you can see now that we can actually move this line. If I come here and move this line, you'll see that what am I doing? Am I changing? As I'm changing this line, the error is changing. You can see now your SSC is 34.9. Now, if I change it, is increasing, the error is increasing. So this basically means that the model is even becoming much worse, right? So, but if I move it up, the error would reduce, right? But what I'm doing right now, remember when I gave you the illustration of trying to get a very good frequency on your radio channel, like you are tuning the knob to get a better frequency. That is what is happening now. We are trying to tune. What we are doing here is that obviously what is being done is not what is being done on the back end, or rather at the back end basically is not a line being moved. What is being done is that the intercept here is changing, right? So you can see here that as I'm moving this line, what am I changing? Changing the intercept. So this y-axis here is where my intercept is. So if I change it here, my intercept here, what's my intercept now based on what we have on the screen? I'm just doing this so we kind of understand this linear regression, exactly how it works, right? So you have a visual in your mind, you have an understanding in your mind. So the intercept here is 1, all right? So if I come back, let's come here. Let's go back to linear regression. So in this place here where we have the formula, this particular parameter here is going to be what replaced with what? 1. We're going to have 1 here, and then plus, then we're going to have our slope. It will be represented here. It's going to replace this particular parameter, and then this x is going to be our variable, right? Our independent variable. So let's go back to our interactive visual. So in this case, our intercept is 1, and as we are moving this line, we are only moving the intercept. We are not moving the slope, right? Or am I wrong? Are we moving the slope as well? No, we are not moving the slope. We are only moving the intercept. But when I come and let me just see. If I come here and click on this red dot and then drag it up, what am I doing? I'm moving both the intercept and the slope. You can see the reason why the slope is changing is because the steepness of this line is changing. So the steepness of the line represents the slope, right? So when it was like this and I was moving it along the y-axis, the steepness is not changing. It is constant. So the slope in this case is not changing. But if I move it in this way, you see that we are changing both the intercept and the slope. So this is basically what linear regression does. It changes the intercept and the slope little by little, little by little, little by little, little by little, until you get to a point where the error is minimized to a point where it cannot be lower than that again. All right. So you can see now that we have this error here. Let's see. Let me see our regression line. So this is what we are trying to get to. If I just come here and change it, so you can see that the line is now exactly the same line. So we've gotten to the point. What we call this imaginary is that our algorithm has converged. It has converged. It has gotten to the local minimum. We've gotten to a point where the error has been minimized. We can't go lower than that. All right. So that's basically what is happening here. So we cannot achieve any better error than what we have here currently. So that is what linear regression does. It changes the slope and the intercept, right? Until you get to a point where the error, when you change it. So let me tell you something. Each time you change this, let me remove this. Each time you change this slope and the intercept, at each point, the error is calculated. I need you to understand the amount of computation that goes into every model building. So at each point, the error is computed. So if it gets to this particular position now with a given intercept value and the slope value, now all the points that we have at that particular position is going to be computed. The error will be computed, and you're going to have error. So with that error, we're not going to, the linear regression algorithm is not going to use what we call back propagation to kind of minimize the error. And then it gets to a new, it uses gradient descent, and then it generates a new slope value and intercept value. And it uses that to calculate another error. And it does the same thing over and over again till it gets to a position where the error cannot go lower than that it is, right? So that's basically what happens in linear regression. So I believe this should just give you a good understanding of what happens in linear regression. So let's move on to today's class, logistic regression. I hope we all understood what I just explained now. So if you want to explore more, the link is on the materials and resources group. I'm going to pin it. So you can interact with it and just understand exactly. Okay, it's pinned already. Just check the pinned messages. Yeah, you should see it there. So today we're going to look at logistic regression. we're going to look at logistic regression. So this is going to be another interesting class. So I need everybody to buckle up. I need everybody to give me their 100% attention. If that's not possible, I need you to give me your 99% attention. All right. So you still need to at least be aware of your environment. So I don't know, but basically just give me your full attention, and we're going to actually enjoy the class. So today we'll look at logistic regression. So logistic regression basically is an adaptation of linear regression. I'm actually going to start with that. You need to have this at the back of your mind, that logistic regression is an adaptation of linear regression. And there is there's something confusing about logistic regression, which is what? The name. Because it has logistic regression, doesn't mean it is a regression, it is used for regression task. Logistic regression is used for classification task. Logistic regression is used for classification task. Right? Just because it has regression in its name doesn't mean it is a regression model. All right. So I'm going to explain all of that, and you're going to understand what it does. But I need you to understand this, because that might come up as a question for those that are just new to that are new to ML algorithms. All right. So today we're going to look at what is logistic regression. As you can see on the outline here, we're going to look at the logistic regression formula. We're going to look at the sigmoid function. We're going to look at types of logistic regression, and we're going to look at evaluation metrics in logistic regression. So today, actually, my plan was to look at logistic regression today, and then tomorrow we are going to look at how to implement linear regression and logistic regression, basically in sklearn using a library in Python. But I'm going to see if we can wrap up with logistic regression as fast as possible and introduce sklearn today, so we can have more time tomorrow to wrap up with it. Because I don't want us to take to take anything from this week into next week class, because we literally are, like, I've checked it, we are 1 week behind, basically, right? So I want to ensure that we kind of cover everything. All right. So that is it for that. So we're going to look at all of this in today's class, and you just start with that. But let's look at this first. So just give me some second. Let me zoom out. Okay, so as you can see on the diagram here, we have a contrasting diagram explaining the differences between these two ML algorithms. All right. So now on the left-hand side, we have linear regression. On the right-hand side, we have what? Logistic regression. So this is a way to kind of just give you the differences between these. So these two are like the regression model, basically. But logistic regression has a slight tweak to it, right? The core of logistic regression is, or the idea behind logistic regression is still the same linear regression, but it was tweaked a little bit so it can be used for classification tasks. All right. So remember, I told you that for classification tasks, all we are working on, or what we are looking at, is to predict what kind of variable. Please, can anyone tell me what kind of variable are we trying to predict, or what kind of output are we trying to predict in logistic regression, using logistic regression? Thank you. We are trying to predict what? Categorical variables. All right. So unlike our linear regression, where we are predicting continuous variable, for logistic regression, we're trying to predict categorical variable. So the formula we use for linear regression cannot be used for categorical variable. All right. Because the y in let me just go back and take you through. The y here is our output, right? This is what we're trying to predict, and this is the formula. So when you compute this formula, you're going to get what? You're going to get a continuous value. All right. So that value you are getting is your prediction, and that is it. So if you use this formula, you can actually predict a categorical variable. You are going to be predicting a numerical, a continuous value, right? But there is a slight tweak to this formula that is going to help us, like, predict categorical variables instead of numerical variables. So we're going to look at in a minute. So that's basically the difference here. And you can see the chart we have here. Um, on our y-axis here, you can see that we have, let's assume the category we're working with are just two categories, 0 and 1. So on our y-axis, our category will just be what? 0 here and 1 here. So you can see that if you plot our chart, you're going to get something like this. So you're going to obviously get all your data points in a either on this 1 line or on this 0 line. There will be nothing in the middle, right? Because we are just predicting categorical variables. If we have 4 categories, it just be 0, 1, 2, 3, 4, and then all the values would be on either of those categories. So, but on the x-axis, obviously, they're going to be spread across depending on the value of your x-axis. So, using a straight line would not make sense, right? Trying to fit this particular data with a straight line won't make sense, right? So that is why we need something else that is much more better, all right, to give us a very a reasonable output. So that is where logistic regression comes in, right? So you can see that the curve or the line for logistic regression is kind of different. It's either instead of being a straight line, it is what an S-shaped line. So this is what we call sigmoid curve. All right. So it's called sigmoid curve. So this is the kind of line that you use in fitting a logistic regression. So it has this kind of shape, right? So it is it's basically biased to each of the category here, right? So if you have any value here and you trace it here, right, you're going to have it to be either of this category. And I'm going to explain something very soon. So in classification tags, what we are usually predicting is what? A probability. We are actually predicting the probability of our output being in either of the classes. Let's say we are working with 2 classes. We are trying to predict the probability of our output being in class 0 or class 1. So the actual output of a logistic regression model is a probability value. I need to take note of that. The actual value of a logistic regression model is a probability value, or the actual value of a classification model, is a probability value. So it does not give you the category straight out. It does not predict 0 or predict 1 straight out from the model. It actually produces a probability, and then the probability is now going to determine where the output is going to fall into, right? So we usually have what we call threshold. So the normal threshold is usually 50%. So the threshold is usually at this point, there'll be a straight line here. So you divide it into 2. So if your prediction falls between 0%, your probability value is between 0 and 1, which basically means what? 0% and 100%. So if your probability value is, let's say, 0.40, all right, if that is your output, then it is going to, which class is it going to belong to in this case? If your probability value is 0.40, where do you think the output will fall in? Is it going to be in the 0 category or 1 category? Based on what I just explained, and just know that the probability value ranges from, or it starts from here and goes up. So it's like in ascending order, 0 here and then 100 here. Exactly. I think we are getting to understand this. So it's going to fall in what? This 0 class, in class 0, right? So if our probability value is what? Let's say 0.71%, which class is it going to fall into? 1. So let me just change the question a little bit. Let's assume the threshold we are using is what? We are using threshold at 70%, right? Threshold is 70%, and our probability value is 0.68. Which class is it going to fall into, or which class is our output going to fall into? Remember, our threshold is what? 70%. those that said 0, you are correct. Those that said 1, you missed it, because we said that the original predictions of logistic regression or classification model generally are probability values. And the way you determine where the final output falls into is based on the threshold you are using, right? So if the threshold is 50%, 50% is by default, right? If the threshold is 50%, then any probability value you have would now be put in either of the classes based on that threshold, right? But if you increase your threshold to 70%, so your threshold now is going to be increased by 70. So you need a higher probability value to get your output to fall in class 1, right? So your probability value, any output that's going to be in class 1 need to have a probability value of 7.0 and above. All right, so that's basically how it works. All right, so just understand the threshold stuff and the probability stuff, because that is the basis of logistic regression. Right, this is just an overview generally, basically, and just to contrast between linear and logistic regression. But we are going to dive into the other details. All right, so let's move on. I really hope you picked one or two from what I just explained now. Okay. So we have let's just look at what we have on the material here. So logistic regression is a statistical method, all right, used for classification problem, as I've explained already. Unlike linear regression, which predicts a continuous outcome, logistic regression predicts the probability of a binary outcome, either two possible outcomes, such as success, failure, yes, no, 0, 1, and all of that. So when you have a problem or a data that has the category or the dependent variable to be binary in nature, binary basically means 2, either this or that. So you most likely be using a logistic regression or any other classification model for that particular task. But I just need to say this: logistic regression can be adapted to working with multiple categories, not just 2 categories. So you can work with 4 categories, 5 categories, and the like. So most of the tasks we have today, they are usually multiple. They usually have more than 2 categories, right? So it is necessary that this classification model can work or can adapt to those kind of data. So this is basically what we use logistic regression for. So used to predict the probability. So as you can see here, probability is a very key word. Let me try to lay emphasis on that. Probability is a key word here. So logistic regression predicts the probability of a binary outcome. So this is what logistic regression predicts. It predicts the probability. I don't know how else to say this, but it's very important for you to know this probability. Now, this is where statistics comes in, right? I told you that for data science, we have an intersection of different fields coming together to make it up. So the fact that we are going to be dealing with probability means that you need to understand what probabilities are, right? So, and every other thing that surrounds probability. So we're not going to be taking on looking at probability as a topic, but I just need you to understand this. You don't need to know every single thing about probability, but it's going to be a nice thing for you to kind of have an idea of what probability is, and just some basic things that surrounds that particular concept. All right. So that's what logistic regression predicts. So these are some use cases of logistic regression. So it can be used in various fields, such as medical diagnosis. It can be used to detect whether a tumor is cancerous or not. All right. Sorry. A tumor is cancerous or not. So the other is basically a yes or no, or a binary outcome. So if the tumor is there, it is what? Yes. If it is not there, it is no. That's basically it. So it can be used in marketing. All right. So I mean, different aspects of marketing, right? It can be used in finance. It can be used in basically many things. So in as I've said, in medical diagnosis, it can be used to predict the presence of a disease. for marketing, it can be used in customer churn. All right. You know what customer churn means? For those of us that are into marketing, is kind of the rate at which customers leave a particular or leave a particular product or stop using a particular product, I guess. Right. So we can use it to predict if a customer is going to use or continue using a particular product or stop or cancel a subscription or not. So those kind of outcomes, right? We can also use it in finance for detecting those that would default on a loan or not, right? So there are a lot of use cases of logistic regression, right? So we can apply it so many places. I feel classification tags are even more common than regression tags. I would argue that actually. But anyway, they both are equally important and very, very necessary to know and understand. So let's just move on. So logistic regression is used for binary classification, as I've said. And there is a particular function that you need to know. Now, whenever I repeat something, just know it's very important for you to take note of it. I've told you about probability, all right? Now, there's something else that you need to know that is peculiar to logistic regression, and it is called the sigmoid function. So the sigmoid function is what differentiates linear regression from logistic regression. So that is basically it. Like, let's just close the class. That's if we are done with logistic regression. All right. So like I can just end it there, but let's just go on so you understand better. So I say again, sigmoid function is that particular thing that differentiates linear regression from logistic regression. Okay. So as I said earlier, that logistic regression is an adaptation of linear regression, right? So that adaptation is what is because of is based on the introduction of this sigmoid function. So what this sigmoid function does is that it takes, you know what a function is basically. A function takes in values, right? Remember from our Python classes, if a function takes in arguments or parameters, as we all know, let's just say a function takes in what? A value and then gives an output, right? That is what a function does. It takes a value, performs some operation on it, and give you an output. That is what a function is, like mathematically, all right? So the sigmoid function does the same thing. So it takes in as its argument or input the independent it takes an input the independent variables and produce a probability between 0 and 1. All right. So we're going to see the formula very, very soon, but just understand this first. So a sigmoid function takes in it takes in the output of your linear regression and gives you a value that is between 0 and 1. So it kind of squeezes the value that you get from that your linear regression function into 0 and 1. All right. So any value you have between 0 and 1 is going to be a probability value. That's what the sigmoid function does. All right. So let me see if I can show you the formula here. Okay, let's just continue first. So for example, let's say we have two classes 0 and 1, right? If the value of the logistic function for an input is greater than 0.5, as I said before, which is what the threshold value, then it belongs to class 1, right? Okay, I think someone pointed out something in the groups, Hazan and Sami. Yes, if it is greater than 0.70 in that case, right? So it should be from 0.71 and above, right? So if it's greater than 0.5 as default, then it belongs to class 1. Otherwise, it belongs to class 0, right? So this is just an extra note here. It's referred to regression because it is the extension of linear regression, but it is mainly used for classification problems. All right. So this is logistic regression in summary. So I believe at this point you should be having an idea. Basically, if you don't have before, you should be forming an idea of what logistic regression is in your head. Okay. So you can see here in the note, in logistic regression, instead of fitting a regression line, we fit an S-shaped logistic function. which predicts two maximum values. All right. Instead of fitting what a regression line, which is what a straight line, we fit an S-shaped logistic function which predicts two maximum values, 0 and 1. So it gives you an output that is between 0 and 1. I hope everyone is still following. Please, I need responses in the live class chat. I hope everyone is still following. Okay. All right. So let's proceed. I just want to be sure that everyone is being carried along. And we have 105 persons on this call, and I think barely 30 persons responded. But anyways, it's fine. So this is basically what logistic regression does, and there are some things I've laid emphasis on that you should take note of. The first one is probability, and second one is sigmoid function. All right. So let's proceed. So now, what exactly is sigmoid function? I'm just going to take you through this. I've explained it already. So the sigmoid function is a mathematical function used to map the predicted values to probabilities. So this is exactly what it does. It maps the predicted values to probabilities. So for linear regression here, let's just come here and let's say we have this linear regression. What this linear regression gives us normally is what? A continuous value, right? So it usually gives us a continuous value. So the sigmoid function takes in, this is just a simplification of it basically. So the sigmoid function will take in this particular continuous value, right, that was predicted, and then squash it to be between 0 and 1. So it can be adapted to binary classification or classification problems generally. All right. So it is used to map predicted values to probabilities. That's what it does. Like, and I think I need to say this like 20 times, right? So you kind of understand it. Like, I need you to, because this is the key, this is the core of logistic regression, mapping of predicted values to probabilities, right? Because for you to have a classification problem, you need to kind of convert what you have to probability values, so you can use your threshold to distinguish between which particular one fall in which class and which one fall in the other class. All right, that's the simplification of classification algorithms, basically, right? Like these, they all follow the same pattern. Okay, so it maps any real value into another value. So this is an explanation of sigmoid function. It maps any real value into another value within a range of 0 and 1. So let's just say you can actually create a sigmoid function in Python. All right, you can actually create a sigmoid function in Python. So you can create a function like def sigmoid function, and then you put your parameter, and then write your code that do this squashing and all of that. So if you give it a real number, it's going to give you an output that is going to be between 0 and 1. All right, that's basically what sigmoid function. That is how sigmoid function works, basically. Okay. Okay. So hope everyone is still following. Hope we are following to this point. I'm thinking, is the attendance on already? Is the attendance on? Okay. All right. So this is what sigmoid function does. Please go ahead and sign your attendance, please. I don't want a situation where after the class I'll be getting complaint that I wasn't able to sign attendance, so this, that, and all of that. So I'm reminding us now, go and sign your attendance. It shouldn't take you a minute. All right, so just log in and just tick your attendance. So as I said, we can actually create a sigmoid function in Python. Actually, let's just do that. Let's actually do that. Let's see. So now, before we do that, let's look at the formula. So the sigmoid function has a formula, right? So this is the formula for sigmoid function here. So this f here is a function. So the function basically takes in as input, and this is the formula here. So this x here is what we are going to be having as our value. This x is the variable, the argument, right, that we are taking in here. So this is the formula for sigmoid function. So if you use this formula, you can convert any real number to probability value. So let's see it in action, right? This is just an extra stuff for you to kind of understand exactly what sigmoid function is. So to create a sigmoid function, we would actually have to use something from NumPy. So let's import NumPy first as np. All right. So just come and say creating a sigmoid function. Right, so def, let's say sigmoid, and let's just say sigmoid. Let me just say sigmoid. So I'll come and say my x. All right. So now this is where you define the function, right? This is where you kind of create the whole. This is where you put out the formula actually that we just looked at now. So the formula is I think so the output should be 1 over. So the reason why we imported NumPy was to use the exponential function. So we'll say 1 plus, let's go back to the formula here. So 1 over 1 plus exponential minus x. So this exponential is, we're going to use a function from NumPy. We're going to use np dot exponential, and we're going to see minus x. All right, so this is the formula for our sigmoid function, and we can just come and say return what output. Okay, so we've defined our function basically. Now, this function can now be used to map real value to probability value. So let's try it out first. So we have sigmoid here. Let's say we have a value of 4. What are we going to get? You can see that we are getting what 0.982 this as our value. All right. So if I change this to 6, I'm going to get this value. So depending on what we put here, we are going to get a probability value basically. So this probability value here really doesn't make sense because this is just random numbers that we're putting here. But when you put in an actual data from your data set, the formula is going to that will be used to basically map the input to the output and kind of just understand the relationship and then give you a probability value that would make sense. All right. So you can use that probability value to you can use it to determine which class the output is going to fall in. We can actually go on and try to create a logistic function that would put another function that will classify that will put our probability values into different classes. All right, but because of time, I'm not going to do that. You can try that on your own. Okay, so you can just say def classify and then put the parameters and all of that, and then use the sigmoid function. If the value from this sigmoid function is greater than 0.5, then add to class 1 and all of that. So you already know how to use your if statement. So you can, I think that should be a task I'll give to you, so you can practice on your own and see how that comes out. So this is what sigmoid function looks like basically. So this is what logistic regression is using to map real values to probability values. All right, so it takes in any real value here and then maps it to probability value. So you can never get anything greater than 1. No matter the number you put, you can never get anything greater than 1. It's either 1 or 0. All right, it's either 1 or 0. You can never get anything greater than 1. All right, so that's just what sigmoid function does. Let's go back to what we have. So this is now a practice session. It's just a theoretical session, but I needed to do that for better understanding. So see on sigmoid function. So the value of the logistic regression must be between 0 and 1, which cannot go beyond this limit, right? So that is why we have that curve that we have, all right? So all this curve that we have here, they are basically probability values. All of them, they are probability values, right? So these are probability values that we have here. So all the predictions of logistic regression originally are probability values, right? So when we actually start to do all these things, like implement them and use the scaling, you see what I'm talking about. All right, so that's about. You can read up all this, the remaining stuff here. So then another thing I need to share. Okay, I think I've explained this. I'm all right. This is talking about the threshold value and all of that. So let's just move on to the next thing that we have here. So we have types of logistic regression. The same way we have types of linear regression. Okay, so we have 3 types of logistic regression. We have the binary or binomial logistic regression. We have the multinomial logistic regression, and we have the ordinal logistic regression. Just for a refresher, how many types of linear regression do we have, and what are they? Quickly, please, just a refresher. How many types of linear regression do we have, and what are they? Okay, simple and multiple, simple and multiple. All right, so I just needed us to have that interaction and all of that. So that's great. We have simple linear regression and we have multiple linear regression. So we have 2 of them. But for logistic regression, we have 3. We have the binary, we have the multinomial, and we have the ordinal. All right. So this classification is based on the category, the number of categories you have in your target variable. For linear regression, the classification is based on what? This is another question to you. The classification is based on what? The classification, as I've said, for logistic regression is based on the number of categories we have in our target variable. But for linear regression, what is that classification based on? I need more people to participate in this. I need more persons to respond. Okay, some persons are getting it, some persons are not getting it. Okay, this is actually very good. So I can actually assess where we are currently and just just bring us back to the correct thing. So fine. So I'm getting 3 responses here. I'm getting some people saying numerical variable, number of independent variables, and which other one? And another person is saying dependent variables. So if you said numerical variables, you are wrong. All right. If you said dependent variables, you are also wrong. So the classification is based on the independent variables, the number of independent variables that we have. That is what the classification is based on. All right. So that is for linear regression. So I need you to get that. Please try to refresh yourself because we are moving ahead. We are going actually at a very fast pace, so you don't get lost in transit. So for logistic regression, we have this theory, and they are based on the number of categories of your dependent variables. So we have binomial or binary. So this is the original use case for classification, right? So in binomial logistic regression, there can only be 2 possible types of dependent variables. So in a case where your dependent variable is yes or no, pass or fail, success to failure, spam or no spam, disease present or disease not present, this or that. We are going to use binary logistic regression. All right. So when you have two categories on your dependent variables, you're going to use this particular logistic regression. All right. I think that's very clear. Now, when you have more than 2, 3 or more unordered, like very, very important, I think I need to bold this for emphasis. Now, these emphases are really important, all right? For multinomial logistic regression, you use it when you have more than 2 categories in your dependent variable, 2 unordered type, right? What do I mean by unordered? So when you have categories like let's say you want to categorize if this particular image or if this particular data is these particular features correspond to a cat or a dog or a sheep. Let's just say we have these 3 categories. This category don't have any inherent hierarchy to it. Like cat is not inherently greater than dog or inherently greater than a sheep. So there is no order to it, right? They can be in any order, basically. So there is no inherent hierarchy. There's no hierarchy to this category. So that is where you use multinomial logistic regression. But when you have hierarchy, like in cases where you have categories like let's say low, medium, high, right? This particular category has a kind of hierarchy to it. So low, kind of in an ordered fashion, you can sense that these categories have an order to them, right? Low is I actually wanted to say low is lower than medium, but that doesn't make sense. But I think you get what I'm saying, right? So low is on the bottom on the lower part, medium is above low, and then high is on the higher side. So there's an hierarchy. There's an inherent hierarchy to the categories, right? So let's say we have something like agree, strongly agree, and all these kind of things that you have in questionnaires, right? So all these kind of hierarchical responses. So those kind of hierarchical categories would require you to use a different kind of logistic regression. So you need to understand the kind of data you have and the kind of task you have, all right, before you now start selecting the particular kind of logistic regression you're going to use. But most likely, you're going to just be using binary or multinomial. Ordinary is not so common, right? It's mostly used, I think you use it mostly in social sciences, right? You most likely not use it in machine learning like that, but it's essential that you understand it. So you use mostly binary and multinomial. No, I'm not saying you won't use ordinal at all, but it's not as common as multinomial and binary. All right. So these are the types of logistic regression that we have. I think this is even more kind of it has more details and should I say complex than linear regression types, but I think with this you should actually understand it. Binary, just 2 categories. Multinomial and ordinal, more than 2, but multinomial works for unordered categories, while ordinal works for ordered categories. I think that should just explain the differences, right? So let's go on. So we have the evaluation metrics in logistic regression. So I think we are almost done. So I think after this, I'm going to go straight to sklearn. I think that is better because we really don't have much time. So we're going to look at evaluation metrics in logistic regression. So we have several evaluation metrics, the same way we have in linear regression, we have it for logistic regression. And these evaluation metrics, they can be transferred, but they can be applied to any other classification algorithm we're going to be looking at, right? In the future, we're going to be looking at other classification models like your SVM, decision trees, and all of that. So the same metrics we are looking at today is the same metrics that we're using. So I'm not going to be explaining evaluation metrics again, right, for classification algorithms, right? So we've explained regression metrics. All right, so today we're going to be looking at classification metrics. So just assume this is classification metrics. So we have several of them. We have accuracy, we have confusion matrix, we have precision, we have recall, we have F1 score, we have ROC score, and I think we have AUC, we have log loss. So these evaluation metrics, they're actually kind of more sophisticated than that of regression. So the regression one is quite straightforward and all of that. But for logistic regression or any other classification model, we actually use a different approach to evaluating those models, right? So because of the categorical nature of our output, we are going to require or we are going to need to use a different set of metrics to evaluate our model. So the first one we have here is what? Accuracy. What we call accuracy. Accuracy is what we know already. So accuracy, basically, you can only use accuracy when you are talking about categories, right? And let me see if I can. Okay, so let's just move on. I will come back to that later. So accuracy is the ratio of correctly predicted instances to the total instances. Very, very straightforward. So let me just come here and see if I can just so we have accuracy as metric. So what accuracy is the way you calculate it is the number of correct predictions over the number or just say total number of your total number of, let's say, your outputs or total, let's just say total instances, total number or total instances. So let's just say, for instance, you have a data that has 1,000 instances. So instances in this case is referring to the same row and observation, right? So this is also a different notation for that. So let's just say, for instance, you have two classes, positive and negative. All right. So for and the total number of our observation is total observation is, let's say, 500. All right. And then the total number of correct prediction. So the way we get this correct prediction is from the model that you built, right? So once you build your model, as the model is being built, like predictions are being made. So let's say we have 500 instances. You're going to also have 500 predictions, all right? So now to get the accuracy, you need to bring out the number of correct predictions, okay? So you have to bring out the number of correct predictions. And let's say, for instance, out of these 500 observations or 500 true value, you are going to have, let's say, 300 correct prediction. So this is basically the values that you need to compute your accuracy. So to get your accuracy, you are basically just going to divide the number of correct prediction over the number of total instances. So in this case, we're going to be having something like, I think, 0.6. So this translates to 60%. So in this case, let's just assume this is our model that we have created. we have 500 observations, and out of those observations, or 500 labels, right? We have 300 correctly predicted labels, and then we use this formula for accuracy, and we compute our accuracy and get 60%. So our model has an accuracy of 60%, and this 60% accuracy is actually not very good, right? So you need to improve on your model so that your accuracy will actually increase, so that your model can correctly predict more of the true labels. So let's say at the end of training your model, you now get to have something like 450 correct predictions, and just 50 of those predictions were wrong. So in this case, you're going to have something like this: 450 over 500, which is going to be, I think, 0.9, and then you're going to have 90%. So this is accuracy. I believe that most of us already understand what accuracy means, but I think it's essential I kind of break it down this way so you understand. So this is how you compute your accuracy, and this is a metric that you use in classification tasks, right? And one thing about classification tasks, unlike linear regression, where you can use you need to use either of the metrics that we looked at. For classification, it is quite different. You use most of these metrics in collaboration, right? So you don't use accuracy alone. You can use accuracy, use confusion matrix, use precision, recall, and all of that to get a good overview of your model performance, all right? So there are a lot of things that goes into interpreting your model performance for classification tasks, right? It is actually more nuanced, and it's actually a little bit, should I say, let me just use the word complex, right, as compared to regression tasks, right? But you definitely get to understand everything that is here. So this is accuracy, right? As I've said, is the ratio of correctly predicted instances to the number of total instances. So for accuracy, it doesn't take account whether that particular prediction is positive or what's negative, right? It just checks everything. So it's going to be something like this. Let's just say you have, this is your true value. Let's just say true value, and then you have your predicted value. So TV is true value, PV is predicted value. So let's just say for the first instance, your true value is what? +1. Then your predicted value, according to your model, is 0. So the second one, 0, already predicted it. So we have 1 here, and you have 1 here, you have 1 here, and you have 0 here. You have 0 here, and you have 0 here. You have 0 here, and you have 1. You have 1. You have 1. You have 1. You have 0. You have 0. You have 0. You have 0. You have 1. So I'm bringing it down to this level so you understand how it is being done. So in this case, this is a particular raw data that is being used to compute the accuracy. So in this case, or even all the metrics you're going to be seeing, this is the raw data that is being used. So in your data set, your Y value or your dependent variable is going to be something like this: 101100. So in case of binary client task, you're going to have something like this. And now your ML model is going to also make its own prediction as well. So the prediction is going to also come in the same format as your label. So this is the prediction, and this is the true value. So this prediction and true value data is now going to be used to compute. So in this case, this first one, is it correctly predicted or wrongly predicted? Let's just go over it together. Correctly predicted, or correct prediction or wrong prediction? Wrong. So this is going to be wrong. All right. Go to the next one. This one is what? Correct. Correct. Go to this one. This one is what? Correct. Go to this one. This one is what? Wrong. Come here. This one is what? Correct. Come here. This one is what? Wrong. Come here. This one is correct. Come here. This one is wrong. Yeah, this one is correct. Yeah, this one is wrong. So it is going to do this for all the 500 instances that we have. So if your data set you have 1,000 instances, or let's say 10,000 instances, it's going to do this particular thing for 10,000 of those instances, and then you're going to compute it. So in this case, we have how many correct prediction? We have 1, 2, 3, 4, 5. All right. So it's going to be 5 over what? We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10. So your accuracy here is going to be 0.5 or what? 50%. Right. So this particular model that you built now has an accuracy of 50%. So these are the accuracies computed. Very simple and very straightforward. All right. So that's it for accuracy. And I think if you understand this accuracy, it's going to be easy to understand every other thing that we are going to be looking at. So we're going to take a step higher now, right, to explaining the other ones that we have here. Now, before we go on, we need to look at something. Accuracy is a useful metric. Now, I know I've told you during the course of this class that you should take note of several things. Now, this is another thing that you should take note of. Please take note of what I'm about to say. Accuracy is a useful metric, but you don't use it all the time. You don't entirely trust accuracy blindly. Before you use accuracy, you need to make sure that your data set is balanced. What do I mean by balanced? You know, in classification tasks, we have binary outcomes. Whether if you're doing binary tasks, you have binary outcomes 0 and 1. So let's say out of 500, let's just do it together. Out of 500 instances, class 1 is 150 and class 2 is what? 350, right? Is this data set balanced or not? Exactly. It is not balanced, right? Because one class has more instances than the other class. So there will be a bias towards the other class, right? So if you're using accuracy, purely accuracy, you might have more of class 2 in that particular data, and then you're going to be having a lopsided, a biased output or accuracy from there. I don't want to go into how that happens, right? But just understand or just know that when you have imbalanced data set, accuracy is not a good metric to use, right? When you have an imbalanced data set, accuracy is not a good metric, right? You don't use accuracy for that. You resort to using other metrics. But if your data set is relatively balanced, and when I mean balanced, I don't mean it should be 250 and what? 250, like it should be perfectly balanced. No, it can be something like, let's say, 200 and 300 is not bad. It's actually it's kind of balanced, right? You don't realistically, we are not expecting it to be perfectly balanced. So this is working. You can work with this actually. So let's say if you have 1,000 instances and you have something like 200 and you have 800, this is imbalance. Like you can't use accuracy for this, obviously. Or let's say you now have 400 and you have 600. This is not bad. You can actually work with this, but you just have to be careful enough. But you can work with this. You can use accuracy for this particular data set. So this is just something that you need to take note of. You don't just blindly use accuracy all the time. You ensure that you know how distributed your classes are in your data set before using accuracy. Right? So that's something to take note of. All right. So that's what class imbalance is. So wherever you hear class imbalance, just know that this is what we are talking about. So let's go to the next thing here. Before I proceed, hope everyone is still following. All right. All right. So let's just go to the next thing here. We have what we call confusion matrix. All right. We have what we call confusion matrix. And I think I said this before that I don't know who named this thing. Like, to be honest, I really don't know. But we're going to explain it and you're going to understand it. So confusion matrix is a table, right, that is used to describe the performance of a classification model on a set of test data. So we're going to all these things. We're going to look at them when we start implementation. Right, but confusion matrix basically is a table that consists of 4 values. Right, we have true positives, we have true negatives, we have false positives, and we have false negatives. So these are the values or the metrics, the values basically that are contained in the confusion matrix. So there's a diagram here that shows us a kind of summarized confusion matrix for us. So you can see it's a table that is divided into 4 sides, right? So on the y-axis, we can have the predicted values, and on the x-axis, we have the actual value. So for each of these particular segments, we are going to compute several values. We are going to compute true positives, false positive, false negative, true negatives, all right? So this is just a simple table. So we have on the y-axis positive, negative, positive, negative. So positive is true positive because this is the actual value and this is the predicted value. Positive, negative. So we have for the actual label or the true value, this is positive here. And then for the predicted value, it was predicted negative. So this is what? False negative, right? So what we are trying to do in confusion matrix is to just display these different metrics for you to see and know how well your model is performing. It's like going deeper, moving beyond accuracy to actually get more detail on the performance. So let's just look at these different metrics one by one. So we have true positives. True positives. What does true positive mean? True positive basically mean the number of correct positive predictions. All right, the number of correct positives. So when you are looking at when you are computing true positive, you ignore the negatives, right? So let's just assume class 1 is the positive class 0 is the negative class, right? So you ignore class 0 and focus on what class 1. And you now look at how many of those class 1 were correctly predicted as class 1. So let's go back to the example that we have here. So in this case, we have class 1 and 0 here. So we have class 1, and in this first one, class 1. We have class 0 here. We have class 1. So we're going to ignore this class 0. We're going to focus on just class 1s here. So these class 1s, they are negative, they are positives, right? So now we're going to say, okay, class 1, we have 1 year, 2 year, 3 year, 4 year, 5 year, right? 5 of them. So out of these 5 positive values, how many of them were correctly predicted? So to compute that, we're going to look at each of them. So for this first one here, it was wrongly predicted, right? So I'm going to come here and say wrongly. Let me just use wrong. For this one here, okay, this one is not part of it. For this one, it's going to be correct. For this one, it's going to be wrong. We'll ignore this one here. For this one, it's going to be correct. Then for this one, it's going to be what? Wrong. All right. Then that's it. So we have just 5 of them. So out of these 5, just 2 out of the 5 were correctly predicted. You understand? So in this case, we have just 2 true positives. That is what true positives mean. So let me go back here. So true positive is the number of correct positive predictions. All right, which means actual positives that are correctly identified as positive. That is what true positives mean. Actual positives that are correctly identified as positive. So there's no other thing to say about that. That is basically just it. So if you don't really understand it now, that's fine. You go over that later on and then you understand it. So when we look at true negatives, all right, true negatives basically in the number of correct negative predictions, all right, the number of correct negative predictions. So for true negative, we're going to come here. Let me make this. This one should be accuracy. This one should be true positive. This one should be true negative. So for true negative, we're going to look at the negative side and ignore we're going to look at the zeros and ignore the ones. So some people are already computing the total. So we have how many true negatives here? This one is correct. This one is no, yes. So this one is what? Correct. This one is what? Wrong. Wrong. This, okay, we have this here. This is what? Correct. And this is what? Wrong. So in true negatives, we have how many here? We have 1, 2, 3. We have 3 true negatives. So let me just put it here. Let me put true positives here. So true positives, we have just 2. True negatives, we have 3. So these are the values that you would be needing in your confusion matrix. So we have false positive and false negative. I'm not going to do that because of time, but I'm doing this just for you to understand exactly how it is being computed. So for false positives are the number of incorrect positive predictions. Okay, incorrect positive predictions. So you can just do the reverse of true positives and you get false positives. So false positive will basically, in this case, we are going to have this one to be correct for false positives. Where is the other positive? This one will be wrong for false positive. But don't get yourself confused. I think you should just use this idea to get. So how many number of false positives do we have according to this data that we have here? So we have one here. We have 1 here. We have 1 here. No, sorry. We have no, false positive actually are, let me come back again. False positive, you're looking at those positive predictions that were falsely predicted as positives. So when you look at the true values and you look at the negative values, or you look at the negative values, those ones that are predicted as positive are the false positive values. So you look at this one here, look at this positive here, we have 1, it is a true positive, right? So this one here is what? A false positive, right? This one is a true positive. This one, okay, this one is a false positive. So we have just 2 false positives here, all right? So we have 2 false positives, all right? While for false negatives, we have 1 here, all right? We have another one here. We have another one here. So we have 3 false negatives. So this is basically how to compute your true positives, true negative, false positives, and false negatives. I'm going to tell you something about this thing. Like when I started learning this evaluation metrics myself, it was a whole lot confusing. I won't even lie. It took me some time to grasp and understand this. So I can understand if you're not getting it immediately, right? But this is essential to know. This is very, very essential to know. So this is what confusion matrix is. And when you compute your confusion matrix, you are going to have the values in this place. So your true positive here will be 2. You have 2 here. You have 3 here, I guess. You have, I think this one is 3 and 2. So if you calculate everything, they should give you the total number of instances. So it should be equal to 10. All right. So this is how you can compute these different values. All right. Exactly. When you're checking for false positives, see, all the true positives, true negative, false positive, false negatives, they are checked on the predicted value. All right, they are checked on the predicted value. So you compare it with the actual values, and then you use the formula to count how many of the false positives or whatever it is you're checking are there, right? So someone said, Gift said, now I know why it's called a confusion matrix. Yeah, actually, I think the name justifies the name is justified. Actually, it can be a little bit confusing, but once you get it, it's going to be very easy to understand. So we're going to be using confusion matrix a lot, right? All these things will make more sense when we start implementing. So it might be seeming or looking abstract at this point. Let's just go straight to the next one. So this is an example here. So we have on your x-axis actual positive, actual negative, predicted positive, predicted negative. So we can use it to compute the values for each of them. So yeah. So let's move on to the next one. So the next metric for classification is what? Your precision metric. All right, precision. So precision is another metric. So we use them precision and recall side by side. So precision is the ratio of true positive predictions to the total number of predicted positives. I'm going to say it again. Precision is the ratio of true positive predictions to the total predicted positives. So you are focusing on the positive predictions for precision. So for precision, you use these values that you computed here. That's why you needed to compute this confusion matrix here. So you need to use these different values you computed to compute your precision. So the formula for your precision and recall is here, right? So this accuracy here. Accuracy is true positive, true negative, which is the same thing as your true prediction over the total. For precision, it's CP, true positive over true positive plus false positives. All right. So in this case, you are basically looking at the positives, right? Because of this false positive that we have here. But for your recall, we have TP over TP plus false negatives. So we are trying to focus on the false negative predictions. So this is how you compute precision and recall. So I just need you to understand it on a higher level. Don't think about it too much. Don't try to overthink it. Just understand that. Just know that we have precision, we have recall, we have confusion matrix, we have true positive, true negative, false positive, false negative. And this is the formula to compute precision, and this is the formula to compute recall. Don't overthink it because it's going to just it's going to scatter your head, right? So, but just take it step by step. So that is basically what we have. We have the accuracy, which I've explained. We have the confusion matrix, which have those 4 values that we've just explained. So from this value that we have here, true value and predicted value, you can compute all of these things that we are looking at, all of these metrics, right? So now it's essential that you understand where to use recall and the importance of precision and the importance of recall. So precision is, as I said, is the ratio of true positive predictions to the total predicted positives. While recall is the ratio of true positive predictions to the total of actual positives. Now, precision is focusing on only positives, while recall is focusing on precision is focusing on the total predicted positives, right? So if you come here, you have 1, 2, 3, 4. You have 4 predicted positives. So this is the positives that precision is focusing on. While recall is focusing on the total actual positives. So it's focusing on these actual positives, the true value. So precision is focusing on the prediction, the predicted positives, while recall is focusing on the actual positives. All right. So that is basically the difference here. So recall is the ratio of true positive predictions to the total number of actual positives. So you have to get the true positive prediction. So we've seen how we can get TP here. All right. So in this case, we have how many true prediction, we have just two true positive predictions. All right, that is true positives. So, and for recall, we have true positives over true positive plus false negative, which is actually the as we have here, the total number of actual positives. So it's focusing on the true values, right? The actual true values and not the predicted, the actual positives and not the predicted positives, right? So this is going to just confuse you a little bit, right? It's fine, like it's actually expected that it sounds and looks confusing, right? But I think it should make sense as you look at it the more and as time goes on. So that is basically. I mean, I don't want to dive too deep into it, so we don't get it all over the place and then it scatters your head. But I just need you to understand these metrics that we have for accuracy. So we have accuracy, we have for classification rather. We have accuracy, we have confusion matrix. So it's in this confusion matrix that everything became confusing. Right now, it's making sense. It makes sense why it is called confusion matrix, right? So we have the true positives, true negative, false positive, false negative. Once you understand these four values here, these four things that are here, every other thing is going to be easy for you to understand. All right. So because most of these metrics that they are derived from these values. So once you can understand how these values are gotten, these ones here would be easy for you. All right. So just try as much as you can to understand this. That's why I took my time to just write it down manually and just show you how we can get each of those values, right? So let's move on so you don't get confused more. So we have, as we have said, we have precision and we have recall. So we have F1 score. And as I said, it's essential you know when to use precision, as essential you know when to use recall. So precision is important in situations where the cost of false positives is high, right? So where you want to prevent false positives, like in cases where you have like you have a model that predicts whether someone has, or let's say in spam detection. I'm going to come back to that. I'm going to go back to that disease detection. I think that one is for recall. In spam detection, you know, our email, Google Mail actually uses a model to classify spam or not. So when someone sends you an email, it passes through a model actually, and that model classifies that particular email as spam or not spam. All right. So, you know, you don't do it manually. So when you go to your email, you can check spam and you see a lot of emails that you've gotten. And your normal email, you have a normal email. So the entire process is being regulated by a classification model. All right. So that we call this spam detection. So in this particular case, where you want to minimize false positives, right? So in this case, false positives basically mean in spam detection, the positive is what? Spam, and the negative is what? Not spam. I need you to understand that first. In spam detection, the positive values are the ones that are spam, right? Which is going to be 1, and then the negative category is going to be non-spam, which is 0. All right. So for false positives are those email that are classified as spam but are not spam. So let's say you applied for a job and then they sent you an email telling you that, okay, you've been successfully selected as a potential candidate. That's a very, very important email. All right, that's a very, very important email. But then the spam detection model classified that email, which is not spam, as spam. So in this case, it's going to be something like this. Remember that spam is what? 1, category 1. Non-spam, not spam is what? Not spam is what? 0. So let's say the actual value, the actual category, actual value for that particular email is what? Not spam, which is 0. Okay, so that email that was sent to you, right, like has been accepted for a job, as a candidate for a potential job, is not spam. So the value is 0. But your model predicted it as predicted value. Your model predicted it as what? Spam. So what do you call this value now? Is it false positive, false negative, true positive, or true negative? This one that is here now, is it true positive, true negative, false positive, or false negative? I need more answers on this. I'm actually just going to take the rest of the time explaining this thing. We'll kick off with SQLN tomorrow. I need us to understand this. Okay, some persons are saying, I think the two responses I've seen so far are false positive and false negative. All right, so I want us to understand something. When we say, those that are saying false negative, you are wrong. This is a positive value, so it cannot be negative. So either you are saying true positive or false positive. So if you are saying negative, you are just out of it entirely. So this is a positive value, a predicted positive value. So it is positive first. So now the question you'll be asking, is it false positive or true positive? Is this positive, this thing that has been predicted as spam, is it actually spam, or is it not a spam? Or is it a not spam email? So based on this, you will now compare it with the actual value. So the actual value for that particular, the actual label of value for that particular data is what? 0, which is what? Not spam. So the fact that this original value is a negative value and the predicted value is a positive value, automatically it means that it is what? False positive. The positive is not true. It is false. That's what it means. It is false positive. So that's what we are trying to say here when we say that when we try to reduce the cost of false positives, we focus on precision. All right? We focus on the precision metric to reduce. So if you're building a spam detection model, you focus on making sure that the precision value is high. Once the precision value is high, that means you've minimized false positives. So that means you are not going to be the important emails are going to be actually entering your email at your inbox rather than going to spam. So you don't miss on important things. You understand? That is the importance of precision. I hope we're all getting this. All right. So just use this email illustration I just used now to kind of understand precision. So in precision, you are trying to minimize the costs of false positives. Okay? You are trying to minimize it. That's when you focus on precision. So now let's go to recall. Recall is another one that is used, all right? So recall is used when you want to reduce the false negatives. That means the cost of false negative is dangerous. You don't want to have a situation where the false negatives are high. In situations like disease detection, all right? So let's assume you have an algorithm that detects whether someone has a particular disease. Let's say a person has cancer or not. So you want to create a model that predicts whether a person has breast cancer or not. So there was a model, an AI that was created recently. I think either late last year or early this year. I can't really remember the exact date. So the model was able to actually look at X-ray images of the breast and tell you whether potential cancerous tumor or not. It was actually very, very accurate. So let's just assume we're using that kind of model, right? We would, in that case, it's a classification task, right? So we're going to try to use this metric that we're looking at. So in that case, we are trying to reduce false negatives. So in this case, what does false negatives mean? Let's go back to this our notebook. So for recall, this is recall, right? In recall, we are trying to reduce false negatives because high false negatives are a high false negatives is actually let me precision here. Precision and recursion. So we're trying to reduce false negative because high false negative values are dangerous, or is dangerous. Anyone? Okay. So now let's say the actual value. There is a particular breast MRI image or X-ray image, and for that particular data, the actual case or the actual value is what is positive. All right, that means that person what has breast cancer, has a breast tumor that is potentially cancerous. Let's just say it has breast cancer. All right. So this is the true value of that particular instance or that particular person data. Now your model predicted, let's say predicted value is what? 0. So this 0 now is what? Is it false positive, true positive, false negative, or true negative? Quickly. Why do we keep saying true negative? I'm glad that nobody's saying positive, first of all. That's a step forward. We are making progress, right? At least nobody's saying positive again. But you can see that this is a negative prediction, right? That is negative first. So now you need to ascertain whether it is false negative or true negative. If you say false negative, if you say true negative, you are basically saying this value here and this value, they are the same thing. That's what you mean when you say true negative, right? In this case, it is not true negative because the predicted value is not the same thing as the actual value. So this negative is false. It is false. Like it is false. That is what we mean by false negative. All right. So I wish we had more time. I would have just given us use this to ask us several of these questions so that we can kind of understand what these things, how we can interpret this. So let's just move on with our recall. So recall is trying to reduce false negative. So this false negative, what does this false negative mean? It means that even though the patient has cancer, the model predicted it to be negative. Now, do you see the potential implication of this prediction? Someone has a disease, but the model they are trying to use tell you that there's no disease. What will happen? That person will believe that, oh, I don't have cancer, or I don't have disease. But in actual sense, they have that disease, right? So they will go home feeling that, I'm free, I don't have any disease, not knowing that thing is killing them. And before you know it, the stuff takes over and the person begins to calm down. And unfortunately, the person dies. You can see how impactful false negatives is in this particular scenario. So recall, the recall metric in this case is used to focus on reducing those false negatives. So your model will not be giving you false negatives. So choosing between precision and recall will depend on the particular task or the particular domain or the particular problem that you are trying to solve with your model. All right. So in spam detection, you are trying to reduce what? you're trying to reduce false positives. In disease detection, you're trying to reduce false negatives. So you use precision in spam, you focus on precision, and then you focus on recall in disease detection. So the nuance in classification evaluation is actually there's nuance in classification detection. There are details that you need to look at, you need to pay attention to get a good classification model. It's not as straightforward as a regression model, right? So I believe this should just give you an idea of precision and recall. Let's just move. I think we have some other metrics to brush on before we call it a day. So we have other metrics. We have F1 score. So this F1 score basically is just a combination of precision and recall, right? So you can see here, F1 score is a harmonic mean of precision and recall. So it kind of combines precision and recall together and giving you a value that kind of balance both of those concerns, all right? So F1 score is another metric. So it is useful when you need to balance precision and recall. We have ROC. ROC is just a curve that kind of displays the metrics and compares metrics across either different thresholds or different models, right? So when I think we're going to get to a point where we're going to build several models for a particular task, and we're going to compare their performance using ROC curve. So ROC curve is that your guide. So as you can see here, we have a curve that shows you this. So ROC curve uses a metric called AUC. AUC is another metric, so they go hand in hand. All right. So there are a lot of things happening in this. I would advise you that you go after this class. You either listen to this video multiple times, right? Because it can be elusive, or you look at this material and look at each of these things one after the other. Try to break it down. Take your time. Don't rush it at all. This is not something that you rush. All right. So that's why I said the theoretical aspect of ML is more tricky, right? It takes more time for you to understand it than the implementation. The implementation is straightforward. Like anybody can just implement it, right? Write this code, model.fit xy, blah, 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 all of that. But understanding how to approach the problem and how to evaluate your model is what distinguishes you as a data scientist. Like you have an understanding of what to do, what to tune, what to focus on, and all of that, all right? So this thing is a very important aspect, very, very, very important. So AUC is called area under the curve. So it's a metric that it goes hand in hand with ROC. So you usually see it as AUC ROC, all right? AUC ROC. So that's what they usually call it. So it's between 0 and 1. So obviously 1, it basically means the particular model is a perfect classifier. Y0 mean is Y, I think 0.5. You barely see 0, but less than 0.5 basically means just randomly guessing, right? So we're going to, don't worry, we're going to actually like implement all of these things. And when we're implementing it, if you don't understand it now, at that point you will understand it. But as long as you listen to what I'm saying here, all right, I'm actually promising you that if you listen to everything I've said so far, even if you don't understand it as you want to understand it to your satisfaction, when we are implementing it, it will make sense to you. Like it's going to be like a light bulb. Oh, this is what the tutor was saying the other day. Oh, that is exactly how it is going to be. All right. So I'm actually promising you that as long as you're listening. So that is it for AUC ROC. So it's a curve. We're going to be plotting this curve, right? Definitely. When we start doing all of those things we'll be doing. So as the curve, the aim of the curve is so in this case, you can see we have 3 classifiers, right? The classifiers in this case, 3 models. So in this model, the model that is closest to this point here is the best model, right? So this blue model, this blue line, this yellow line, this green line, and this red model. So this one here is the best model because it's closer to this particular point here. This yellow one here is really not that good, right? So that is basically how you interpret your ROC curve. So you can see here, a ROC curve that goes towards the top left corner indicates a better performing model, all right? So this is what we have. We have in this place true positive rates and false positive rates. So all these things still boils down to the confusion matrix values that we looked at. And then the AUC, you'll be able to compute the AUC. We'll look at that as well. We also have the log loss, logarithm loss. So this is also a metric that measures the performance of a classification model, where the prediction imputes a probability value between 0 and 1. So log loss is a metric. We are also going to like explore all of this. So just take note of these metrics that we've looked at so far. I'm going to, I think I'll send a video this night explaining some of these metrics, like just throwing more light and giving you a fresh perspective, basically. So that is it for the metrics that we have in accuracy. You can see that this is actually, I would say, more interesting, in quotes, than linear regression. So that's it, basically. So let's just summarize what we've learned so far. So we have these metrics. We have accuracy, precision, recall, F1 score, ROC score, AUC, ROC, and then log loss. So for accuracy, we use it when classes are balanced and you want a general performance measure, right? It's a good first start, right? Good first start. So precision is when the cost of false positive is high. So this one is problem specific, right? So depending on the problem you're trying to solve, it will determine whether you focus on the precision or you focus on the recall, right? So precision, okay, I didn't tell you, precision value is between 0 and 1. That is 0% and 100%, all right? That is precision. Accuracy, precision, recall, F1 score, and AUC, ROC, they are all between 0 and 1. So that is 0% and 1%, all right? So if your precision is 80%, that means you are actually dealing with positives very well. Right? If it's greater, so you try to push it to be very, very good, to be at a very good percentage, all right? So the same thing for recall, depending on your problem and all of that. So yeah, so for F1 score, this is when you need a balance between precision and recall. For ROC curve, this is to visualize the trade-off between true positive and false positive rates at different thresholds. So you can also use it for different models as well, not necessarily just threshold. So this thing will make more sense to us pushing forward. So ROC, that is AUC ROC, is to help you get a single measure of the performance across all thresholds. So it's also a performance measure as well for your classification model. And log loss is also a metric. I think we're really not going to make use of this log loss a lot, but it's important that you also take note of it. It's needed when you want to measure, evaluate your predictions as well, your probability predictions. So that is it for logistic regression and classification metrics. I think this is actually a lot to take in, right? Like I know why I'm saying this, because it's something that can be challenging to understand at first. But please don't think it's something that you might not be able to understand. Just take your time. You definitely understand it. The examples I've given, try to go over the video again if you can, and try to go through the materials as well, and all of that. Since you are going to, and then once we start implementation, I'm going to just be kind of going back and forth, bringing back the metrics, trying to explain it and all of that. So everything will definitely make sense, like at the end. All right, so that is it for logistic regression. So you can see the classification metrics here: accuracy, recall, precision, ROC, and all of that. So not just for logistic regression, for other classification algorithms as well. All right, so that is it for logistic regression. We are going to be going straight to how to use sklearn for logistic regression, tomorrow's class. All right. So sklearn, we're going to recap on logistic regression. We're going to look at we can train a binomial logistic regression, and we can train a multinomial logistic regression, and how we can evaluate our model. So this material is already available for us. So we're going to go over all of these, the steps in building a logistic regression model, load your data, split your data, train your model, evaluate it. So we're going to go through each and every one of these steps, and then it's during this evaluation that then we're now going to like pay close attention and explain and just throw more light on what we've discussed today already. All right, so it's going to be interesting, trust me. Like, it's going to be a very interesting class moving forward. So just stick with us, don't give up yet, and yeah, you're going to definitely come out strong. So we will draw the curtain here at this point, and I'll give room for questions. If anybody has questions, please raise your hand, and yeah, just indicate by raising your hand. Question. Anyone with question? Okay. I just want to believe that we need more time to assimilate. So and if there's any question that comes up later, then you can just hit me up on the chat, not DM, please, not DM. I barely reply DMs because avenues have been made for us to lay our complaints. So class reps, we have assistants, and all of that. So that's going to be for today's class, and I just want to say some few things before I wrap up this class. I have been seeing some very, very, very like encouraging and interesting posts on LinkedIn so far. I think we are getting to engage more. We're getting to put ourselves out there. And first off, I must commend our assistant class rep, Nigeria. She has been doing really well. I don't know how many of us are following our connections with her, but she has actually been putting herself out there, and it's a very, very good thing, trust me. Like, people get to see you, people get to just like notice you. Like, they might not say anything, they might say something, you might see them liking it, you might see them commenting, or they will not say anything, but definitely people are just looking at you and all of that. So just keep on doing what you're doing. It's going to be of benefit to you as well as people around you as well. So I see some other persons doing it as well. Justice has been doing it so far, which is great. Gideon too posted, and like I can't mention everybody, like, but I'm seeing a lot of posts, and it's very, very like encouraging and nice to see all of that. So please, I would tell you to keep it up. Don't relent, keep persisting, keep learning outside of what we are learning here, right? It's going to definitely pay off, like definitely pay off. So today's class is a very interesting one, right? I believe I'm not lying. So we are going to definitely scale through all of this. So machine learning is not I won't really say it's that easy, but it takes some persistence and some kind of curiosity, level of curiosity and determination to just break through. Right. So, and that's what I require from us, and I believe we are all we're going to scale through as we be prepared. So enough of the pep talk. So we'll be calling this class, we're going to be calling it a day at this point. And I want everyone to write out or to like note down what they learned in today's class. No matter how basic it is, no matter how small it is, I want to see what you learned in this class today, all right? So whether it's one thing I said, or maybe just something I said in passing or whatever, just tell us one thing that you learned in this class, right? So you can just take your time to think about it. Okay, so far, what did I actually pick? What did I, like the time I spent, the 2 hours I spent in this live class, what did I pick from it? Like you should be able to like pick out something, right? So thank you very much for your time. We're going to continue tomorrow. And tomorrow is going to actually make more sense to us because we're going to be implementing what we have learned so far. And also, this week is going to be the last week for assignment. Your project is going to start from next week, right? So it's going to go alongside our classes, right? So the project is going to be available from next week, right? So you have 2 weeks to do your project. We have just 3 weeks remaining for, I think we have this 10th week. So we have 2 weeks remaining for this program. So we're almost done, actually. We are actually wrapping up. So yeah, we are almost at the finish line. Don't give up, right? So that's it. This week assignment will be the last assignment, and then we're going to start our project. All right. So thank you very much, and do have a good night rest. See you tomorrow.